What's up, chem peeps? Time for some more chemistry. In this vid, we are going to explain how the solubility of a substance can be understood in terms of chemical equilibrium. Breaking it down, you want to be able to interpret data regarding the relative solubility of salts involving common ions. Dos. You want to interpret data regarding the relative solubility of salts in acidic or basic solutions. Alright, so we're going to start with the common ion effect. A salt is going to become increasingly less soluble in a solution that contains one of its ions. We can use Le Chatelier's principle, and it's called the common ion effect. As an example, to help understand this, some chloride salts are less soluble in seawater that contain chloride ions, a common ion, than pure water, since the presence of chloride ions will force the equilibrium to the left or solid side. Think about lead 2 chloride as an example. In seawater, there's going to be a bunch of extra chloride ion. It's like adding product. And what does Le Chatelier say? Adding product, we're going to shift away, making that salt less soluble. Common ion effect. Similarly, salt containing ions that can act as an acid or a base can have its solubility affected by the pH. For example, let's take a look at iron 3 hydroxide, a base. It's going to be less soluble in basic solution. Again, think about it in terms of Le Chatelier's principle. Here's my equilibrium for iron 3 hydroxide. If it's in a basic solution, there's going to be a bunch of extra hydroxide, which is going to shift this equilibrium to the left or the solid side of the equilibrium, making it less soluble. However, iron 3 hydroxide will be more soluble in acidic solution, since the acidic hydrogen ion will remove that hydroxide ion from solution, and therefore Le Chatelier predicts we'll shift to the right or the ion side. Again, my iron 3 hydroxide equilibrium, if I put it in an acidic solution, the hydrogen ion is going to react with hydroxide and essentially remove it. Le Chatelier says we're going to shift then to the right, making greater amount of ions less solid, more soluble. Let's continue with some molar solubility in KSP, this time with some common ion. Oh yeah. What is the molar solubility of calcium fluoride in a solution containing 0.100 molar sodium fluoride? The KSP of calcium fluoride at 25 degrees Celsius is 1.46 times 10 to the minus 10. First, let's write an equation for the dissolution calcium fluoride in water. Done. Notice the stoichiometry in our equation. For every one calcium ion, there are 2 fluoride ions, based on the ratio of ions in the formula. Ice table. Boom. Drop the solid calcium fluoride. Not going to show up in our KSP expression. Initially, we have no calcium ion and no fluoride ion. Oh, but do we? This is not pure water. We are placing this into a solution of 0.1 molar sodium fluoride. So in fact, initially it's 0.100 molar fluoride ion. Common ion. Define our changes in terms of x, increase value of x, increase value of 2x. At equilibrium, we'll have x for calcium ion and 0.100 plus 2x for fluoride ion. Again, we already have a bunch of fluoride ion in solution. Write your KSP expression. Boom. We know the value of KSP to be 1.46 times 10 to the minus 10 for this salt. Boom. We've defined the equilibrium concentrations for calcium and fluoride ion. Boom. Now, before I go any further, I'm going to do the X is small approximation. And the reason why I'm going to do that is because my initial concentration of fluoride ion is more than 1,000 times larger than my value of KSP. So I can be pretty confident that the change in fluoride concentration isn't going to be very significant. Now, we can always check that at the end, but a good rule of thumb is simply to compare your initial concentration and KSP. If they differ by a factor of 1,000 or more, you're good to go. X is small approximation. Initial concentration of fluoride ion and KSP differ by more than a factor of 1,000. Boom. Notice how that's going to make this problem a heck of a lot easier. Don't forget to square it. Jump to your calculator. 1.46 second e negative 10. Close parentheses. Divide by parentheses. 0.100 close parentheses squared. Answer. X equals 1.46 times 10 to the minus 8 molar. Boom. Molar solubility of calcium fluoride. Again, we're solving for X, but because the ratio of calcium ion and calcium fluoride is 1:1, X is also the molar solubility of calcium fluoride. It's how many moles per liter we can get dissolved at 25 degrees Celsius. Now, you might be saying to yourself, whoopity-doo! But let's determine the molar solubility of calcium fluoride in pure water. Equation, ice table, drop the solid. Initial 0 and 0 in pure water changes plus X plus 2X. At equilibrium, X, 2X. KSP expression, boom. We know the value of KSP. We've defined our equilibrium concentrations in terms of X. When I simplify, I get 1.46 times 10 to the minus 10 equals 4x cubed. Jump to our calculator. 1.46, second E, negative 10, close parentheses, divide by 4, insert, math, 4, seconds, insert. Boom. So notice, in pure water, the molar solubility of calcium fluoride is much greater than the molar solubility of calcium fluoride in 0.1 molar sodium fluoride. Here, there's some common ion, the fluoride ion. Think of Le Chatelier. We're shifting this equilibrium back to form solid, so not as much of it is going to dissolve, and therefore the molar solubility is lower. Boom, done.